Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on September 8, 2025, which was about 7 days ago. The headline result is a first of its kind, a vision-language diffusion action model that turns mask diffusion into coherent robot action sequences, delivering state-of-the-art performance in simulation and on real robots. The paper is titled LLaDA-VLA, Vision Language Diffusion Action Models, and as we will see later, the implications for robot policy learning are quite significant. The method narrows the domain gap with localized special token classification and decodes actions hierarchically for consistent multi-step control. On X, a robotics account highlights the release, linking project and paper, and emphasizes diffusion-based vision language action control with hierarchical decoding and special token classification, drawing solid engagement with about 295 likes. Alright, the previous discussion highlighted diffusion for action generation. Figure 1 contrasts two pipelines. The left panel shows an autoregressive VLA that emits action tokens one by one, which creates a strict left-to-right dependency and limits flexibility. The right panel shows LLaDA-VLA, using a large language diffusion model that starts from mask tokens and refines them in parallel, so many action tokens update together. The legend clarifies image, text, action, and mask tokens, which makes the parallel refinement process explicit. Okay, the previous figure contrasted autoregressive and diffusion pipelines. Figure 2 shows the full system. The vision encoder and projector map the camera view into the text token space, which is concatenated with the instruction and mask tokens. Then the large language diffusion model predicts action tokens. Localized special token classification restricts prediction to a small action vocabulary, which simplifies adaptation. The right panel illustrates hierarchical action structured decoding that iteratively remasks at the action level and at the token level based on confidence. So, the previous figure illustrated the decoding mechanics. Table 1 reports what that buys on the simpler ENV robot tasks. The table compares success rates across 4 objectives, and the highlighted last row shows LLaDA-VLA leading every column. The model reaches 56.9, 76.3, 30.6, and 58.3% respectively, which yields a 55.5% average. These gains matter because they surpass strong baselines like OpenVLA and CogACT by notable margins. So the previous table summarized simpler ENV results. Table 2 reports performance on the Kelvin ABC-D benchmark. The table lists how many tasks models complete consecutively, which stresses long horizon consistency because failures reset progress. LLaDA-VLA tops every column with 95.6, 87.8, 79.5, 73.9, and 64.5%, and it delivers a 4.01 average length. These margins over OpenVLA and 3D Diffuser Actor indicate that hierarchical decoding and localized action tokens translate into more reliable, multi-step control. Well, the previous table emphasized long horizon reliability. Table 5 isolates where the gains come from. The table reports task completion rates across 5 consecutive steps and the average episode length, so it separates early wins from sustained control. The baseline managed 86.2% on the first task and only 2.64 average length. Adding localized special token classification lifted the average length to 3.43, which indicates easier adaptation. Adding hierarchical action structured decoding reached 4.01, with stronger percentages in every column, showing more coherent trajectories. Wrapping up, 2 takeaways stand out. Localized special token classification narrows the vision to action domain gap, and hierarchical action structured decoding makes multi-step control coherent and reliable. The broader implication is clear. Mask diffusion can power practical robot policies, not just generative media. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.